Hello. Let me mute your voice. Hello.
Hello.
Hello. Some problem is there, I think. Trying to. Uh, Hello. Hello. Hello.
Hello, hello.
Am I audible?
Yes, yes.
Okay. Okay. There might be some problem. Trying to. Now I think it's fine. So So let's begin this week's discussion session. So this week's discussion would mainly let me check what is early of. So mostly this week we have seen that the demonstration section has been mostly covered. Uh, the overall aim of this of the preliminary discussion of any of the last 8 weeks that we have done or we have completed. So based on those means those were the theoretical background, and based on those theoretical background we'll now see how things work in practical in a practical sense. Okay, so that we have mostly seen where the converter technologies, how their implementation in the modern or smart grid renewable uh, techniques, renewable integration part, that we can see how these things have been covered in this how to implement them in practical sense. Those things have been discussed. Okay, so initially it was some microgrid scenarios were also being discussed, and EV demonstration, solar power generation based renewable integration in the power system based demonstration, wind integration based demonstration, etc. So accordingly, we'll just ponder upon those topics one by one, and firstly we'll have a summary session, and based on this summary session, we'll have some discussion on the question and answers. So for the time being, let's start with this week's discussion. Okay. So mainly we can see that solar inverter, what the solar inverter application. So since we are primarily focusing in this mo- module, that solar solar power generation. So in the microgrid architecture, what we need to observe is that how these solar uh, panels are being integrated, and how the output that we get as a part of uh, which is the DC power output. So we cannot directly integrate them before, because that's a variable DC component. So we need to assimilate the variable DC. We need to transform to fixed DC before feeding to the grid. Okay. So the working principle of the solar inverters that converts the DC power from, also we will have to, if the grid we are talking about is AC. So in those cases, what we will have to see is that uh, the solar inverter feeds, if they are feeding the AC grid. Okay, so there can be instances where the solar power needs to feed the AC grid. So, so forming grid support is our major aim. Means now we'll have to talk about the grid support mode of operation. Okay. So that means the solar converter should be, means the operation would continue to start when, if and when there is a proper synchronization between the AC frequency, AC output, means after the conversion, DC-AC conversion, this frequency and the grid side frequency. This is the grid, so there would be a point of common coupling. So here, before the coupling, this side frequency and this side frequency should match, or at least be within a prescribed uh, operating range, so that the operation can be considered to be legit. Okay, so here we can see that, and we already know that the IV characteristics of the PV uh, mostly follows the curve like this, where we can see the current. Here it is I, here it is V. Okay, and here it is the VOC, and here it is ISC. So this is the point. This is the point of maximum power point tracking, MPPT. So what we try to do is that we try to extract the maximum power from the solar and the wind, solar or wind or the renewable sources. Okay. So if we see the power, we can observe that at this point of time, this power is the maximum. So we need to use this much amount of power. So this is the maximum power point. Respectively. So there can be scenarios where, uh, since here we would be mostly trying to discuss about the hardware setup or hardware control. So firstly, here we can see that here it's a single conversion stage. So single conversion stage, and the PV panel is connected to the DC link, or we can say across the, directly connected across the DC link. Okay, and here in this case, here we have a dual two-stage solar inverter. So here we have a dual converter stage. Dual converter stage. Okay, so PV panels are connected directly to this DC-DC stage. So PV panels to DC-DC stage, and the output of this DC-DC stage is connected to the DC-AC grid. So here losses are high, but the regulation, the control over, or regulate the control that we get, or to regulate the system, this is much higher. So better regulation, much better, let's say. So that's the advantage, one advantage here. So here we can see a single stage solar inverter control, where first it's the MPPT stage, then we have a DC link DC link voltage control, where the MPPT is obtained by maximum power point tracking of this V and I. Okay, so delivering this V and I as discussed previously, we get to find the maximum power point, and accordingly we can see that DC control, DC link voltage control, we obtain the current value as ID star. Okay, and after that here we have a phase block loop. So to uh, because since we are taking AC as output, so we'll have to synchronize somewhere. Okay, so to achieve this synchronism, we have a phase lock loop, so that the feedback is fed, and accordingly the pulse wave modulation PWM, the modulation, the pulses would be accordingly injected, so that the frequency of operation becomes same or similar to that of the grid, because it has to connect itself to the grid. Okay, so and also we have another dual stage inverter mode. So here in the first stage, the DC stage. So it has one DC stage and another DC stage. Whereas in this case, it is only DC AC stage directly. So the variable power output, or the variable DC that we can obtain from the solar or solar panels. Okay, so that needs to be directly converted to AC with the variability in place. And but here also this one is also variable, but the advantage is that the output first it is made a smoother output, and again from the this allows a additional regulation, means we can control the trigger pulse values of the pulse of these what we say IGBTs. Okay, so the AC is of the IGBT convert, or we can also say the power electronic devices, power electronic switches. So since we can vary the angle, so that's why we get a better regulation as an output, or the regulation or the point of regulation becomes much more open. So DC stage mainly acts as a boost converter stage. They are the boost converter, and here it has the control feature to the regulate the output side power. Okay, so this is the advantage that we get from this solar mode. So based on this, some hardware setup has been developed, and using this polarity, and using this hardware setup, the demonstration has been performed, and how the controlling this converter triggering helps in controlling the output side power qualities, how to improve the voltage profiles by controlling the reactive power, because here reactive power control is provided. So next comes the wind. So here's the basic arrangement of wind energy, where we can see that the kinetic energy of the wind gets converted to the electrical energy. So here we have the wind turbine, where the controlling by controlling the pitch angle, we can uh, control the output of this system or output of this power to the grid. Okay, so here we have a gearbox because uh, we'll have to rotate the machine or the generator at a speed so that so that the output, or we can say that at the rated speed. But for some point of time, there can be instances where the wind is flowing very slow, and generally those are instances that we see. So in those cases, there's a gearbox which this side is the slow, or the tooth of these gears are more. So low speed to high speed conversion stages, and accordingly the generator, the shaft, same shaft is connected. As you can observe, this is the same shaft as connected to the machine. So accordingly the three phase, the AC power is generated, and this AC power, which is again a variable AC power because it is dependent upon the variability of the wind. So that's why the power converter that we can see here converts the variable power output to a constant before feeding to the transformer, and which is then fed to the grid. Okay, so mostly what we can see is that the wind velocity that we know, the wind power that we get is somewhere at rho a v yes, vq and cp, which is a function of theta. So by also this power can be as the control feature of this power can be achieved by utilizing the pitch angle. So here we can see the grid side control or grid side operation where the this is a DFIG based operation. Okay. So in this DFIG based operation, there's a gearbox, and this is the rotor side converter, and this is the grid side converter. RSC stands for rotor side converter, GSC grid side converter. So by whenever the output has to be met, so in those cases, based on this initial phase where there is a grid support mode of operation, so in those cases the power can be taken from the grid to initially provide the uh, field, and after when those point is achieved, so in further cases when it is feeding power to the grid, there can be control strategies to uh, provide necessities to the grid. So again, the operation grid forming mode of hardware operation has been demonstrated where the wind power system is emulated. Okay. So accordingly, how the variation affects the total entire operation, that can be observed. Okay. Now coming to the other demonstration section where it is dealing with the battery management system. So firstly, the need of battery uh, can be heavily observed. Means as we also had discussion what is the need of involving battery into the modern day or present day smart grid scenario. Okay, so first of all, since we are integrating renewables into the system, okay, so there can be cases where the renewables have the capability to deliver power, but their variability. There were instances that we discussed that there are two peaks, one morning peak and evening peak. Okay, so in these morning and evening peaks, we generally what we observe that we need to our major aim is to flatten our load curves. Okay, to fill these places and to reduce these places. So as we are planning to do this, so for that we need something which can withstand the abrupt changes. Okay, so batteries can serve as a better alternative in these situations. Also, we can also see that the conventional generation system, where we can see these alternators. So these alternators are mainly, uh, or they mainly deliver what we call the real power, but additionally, it has the feature to deliver inertia. It will meet demand, but it also has the feature to deliver inertia to the grid. Now, using the benefit system operation to, to address challenges like sudden loading scenarios. So that means it is providing frequency maintaining support. Because ultimately we'll also have to maintain the frequency. So who would be responsible to maintain this frequency? So in those cases, we see that the thermal power plants have the, or rather we can say the alternators, which will be from hydro. So also we have also discussed some earlier phase stages that we can use we can use palm storage. Okay, so since we are using these pump storage plants, so here using these pump storage plants, they also provide the frequency support in case of sudden abrupt changes in or to deliver the mismatch. Thus, what we can say, we can also need a similar fashion or similar equipment that can provide at least real power support so that the power mismatches which leads to frequency stability, power mismatches which leads to frequency instability, those things can be limited. Okay, so that leads to the foundation of implementing batteries into the system. Now, when we are trying to introduce batteries into the system, so there itself we are trying to develop a procedure or a sequential operation, operational flow with the process that the battery management system development needs a better way out. Okay, so we have multiple techniques, but we'll have to keep in mind that battery management system needs to be properly developed. So what we can see is that in the battery management system, the major aim is to monitor the values of current, voltages, and temperature of each cell. Also, estimation of key features like SOC, state of charge, state of SOC, SOC, and DOD, depth of discharge. So these things, SOC, SOH, using online estimation techniques. Some estimation techniques also we have discussed previously. Some cell module balancing, so active and passive cell balancing techniques. Also computing energy and power limits to pack using limits of the pack using SOC and SOH values. Based on SOC. So what we can see that major currents estimate these stages. Now balancing of the cell is required. So there are various cell balancing techniques. There are passive and active methods, word chart, shunt resistor, and in the passive methods. But in the active methods, we have cell to cell, cell bypass, pack to pack. And in the cell to cell, we have adjacent cell to cell, any cell to cell, direct cell to cell. So these, so there are reasons why cell balancing. So weak cells rise to discharge faster. So this is the point that we need to look at. That we should not allow the weaker cells to discharge faster. So there has to be some, means nothing is ideal. Okay. So if we say that it's the ideal case, then each and every cell would be discharging at the same point of time, charging at the same point. But practically those things are impossible. So there are cases where weak cells tries to discharge faster. So that is one of the primary reason why cell balancing is required. Next, we can keep in mind that cell capacity prematures if this process continues. Okay, so there would be a proper imbalance. Means if we see that two cells are kept, so this much is the charge here, this is the charge here. So if both the cells which are connected in series here are fed to feed some, let's say, load. So the problem that we can observe is that mm, it will be a disaster, okay? Because one cell would be completely drained, whereas the other is completely on. So the control CHIL validation is performed where PC based polarity is used to find out whether the active cell balancing has been done or not. Next, it comes in the EV charging infrastructure. So, firstly, what we can see from this picture is that here we have EV charging infrastructure. So, mostly here we have mode 1, mode 2, control pilot, mode 3 charging. Okay. On-board charger, battery, AC, and the mode 4 charging. So, on the AC part, we have 3 pin, we have type 1, type 2, and here we have a steady mode, combo type 2. So, smart charging concept for optimal EV integration. Smart charging is a time of use pricing without automated control, basic control, bidirectional control, and dynamic pricing with automated control. Now, in bidirectional control, we have V2G, V2H, V2B, and V2A. So there are two modes of operation. V2. So this is the common mode of operation related to vehicle. So we are also taking from the supply from the grid. So electric vehicle would also take supply from the grid. So grid to vehicle. Another one is vehicle to grid. So this is comparatively new, but not that much prominent in tier context, but in the in USA these things have already been framed. So there are instances where in case that the aim of this system is to deliver uh, safety and security. Also, the aim of these inbuilt parameter handling and automation system, or the we can say software modulated system, needs to be developed where the distance, customer location, charging station location, everything for utility distribution versions, more hosting capacity. For utility transmission operators, this is for the distribution. Now for the transmission, there has to be some aim. So smart charging allows some benefits like uh, it can limit peak demand, and for building consumers, so time of tariff or time of use pricing. So these things would be enabled into the system. Scheduling, charge scheduling. So load balancing and charge scheduling we can perform. So that's about the EV section. Now comes the different concept or different discussion topic where hierarchical control. So first of all, we already know what are microgrids. Okay. So by the time if we have any discussion, so we can do, but okay, let's wait for 2 minutes so that this is a fresh part. So any questions out you can ask, otherwise we'll start in 1 or 2 minutes. So So we all know what are the microgrids. Okay, there can be cases where the microgrids can be interconnected. Also, mostly that can be observed in the distribution level. Now, they can also work in standalone mode of operation. Also, this operation can be obtained for a limited time frame. Okay, standalone mode of operation. So in microgrids, because this as an outcome, what is the advantage is that it enhances the reliability of the grid. Okay, now in the microgrids we have many types of renewables integrated like wind, solar, micro hydro, ocean, tidal, fuel cell, biomass, biomass, and we can also observe storages. So these approximately some types that we can obtain or observe. So first, as we all know, so what are hybrid AC/DC microgrids? So here's the AC grid. Here's the operation. So there are physical components. These are the physical components, and only this thing can't work altogether. So for that we have, so these are interfacing component, DC, AC this side, DC this side. This is the interfacing. So as previously discussed. the hybrid microinverter. AC coupled hybrid microinverter. So here it is the AC bus. So everything needs to be converted to AC we can fit into the bus. Here is the utility grid or PCC you can say. Here we have distributed generation which is DC. So DC needs to be converted from DC to AC. And here it is AC generation. So AC DC AC because this is the controlling section. This is the transforming section. And here it is the controlling section. Okay. So the storage element here you also have a bidirectional converter. Here directly AC load and for DC loads AC DC conversion is required. Okay. Similar motion holds true for the hybrid microgrid with DC bus. So here also same motion like DC distributed generation DC DC, AC generation AC DC and storage element bidirectional. The loads are there DC loads AC loads, but these are interfacing converters. So these provides an added support. Okay, so these DC AC converters. Here we have both DC bus and AC bus. So if mostly the loading scenario is AC, so in those cases we prefer to use AC. Sorry, in DC bus, but in some cases where the loads are AC, so and DC both. So in those cases there are the options to use these interfacing converters to deliver the decoupled DC coupled microinverter. Okay, and here it is the AC-DC coupled microinverter. So converters are there on both sides, AC side, AC side. Also interfacing converters are present in case of power exchanges. Here it is the point of coupling. So here we can see the power management strategies for the AC-DC coupled hybrid microwave. So before coming to the power management strategies, so so they help in grid connected for standalone one. Mostly the necessity is required here, the storage necessity of the storage. Okay, so there can be capacity oriented and there can be access oriented. The capacity oriented storage system, they does not have fast response time, but they are used for long term energy balancing. Okay. They are generally used for long term energy balancing. To balance low or oscillations or to compensate the intermittencies. Okay. Now there can be questions like how these things are done. Now pumped energy storage systems are also a part of this. Not only the capacity oriented battery storage, but this is quite similar to pumped storage system. They're access oriented. When we say access oriented, that means devices have faster response time and high frequency component of data. Transients with high power densities. Also, we can say that examples like so there are features. Something I missed is that features of so all the sources. Or we can say subtypes. So this becomes a challenging task. The mode of operation can be grid tied or standalone. The control technique. Here we can observe AC-DC coupled hybrid micro. So here it is a grid connected mode of operation. Here it's a standalone mode of operation. Here is the dispatch tower power output and dispatch power output. DC in the standalone mode we have DC bus voltage control, AC bus voltage control. So in the dispatch power output, the ILCs are interlinking converters. Mounted control interlinking converter DC bus voltage control mode of operation. Now DGs is on AC bus coordination with DGs and providing dispatch power mode. And here in this case, DGACs and DC bus link voltage control mode. The ILCs and DGACs are AC bus and dispatch power control mode. Operates in a ILC power control mode. Now in the undispatched power, ILC DC link voltage control mode operation is followed. DG is both AC and DC bus on MPPT. AC is both AC and DC bus typically charging mode. The standalone mode of operation, here is a DC bus control mode where DGAC's DC bus link voltage is directly extrude method. Example shown. Group control method. Indirectly, so example is power balancing. This AC bus voltage control mode. This is the power based on power voltage control. DGAC and AC are receiving voltage directly on group method indirectly war balancing. So according to the classification, we have decentralized, centralized, we have distributed method. Now we will discuss one by one what are these. In the centralized, communication network forms a basic major poses a major role. Okay, another one is central. Because there can be instances where problems like information exchanges needs to be performed on a better fashion. Okay. Now comes the decentralized. Better communication network is not required. And So what we can observe is that by distributing the control strategies, we have obtained a better advantage of the single usage. So decentralized mainly used for the local variables to control the local variables uh, due to the unavailability of the global variables. In those cases, what we can generally observe is that inaccurate outcomes might be possible. Okay, centralized techniques overcome this architecture, but uh, cost high cost associated. So distributed technique allows global variable access as well as reduced combination. So there can be situations where better or improved power balancing for three-phase microgrids can be achieved. Also, enhanced voltage quality can be obtained. Quality enhancement. Proportional active power sharing between microgrids. So these things can be obtained or facilitated. Voltage levels are also obtained. So overall, some directions of this is because research topic nowadays. So people are doing research in this direction. So there can be cases where uh, cyber attacks can also come into picture. Also, we can say that the system should be self-healing in nature. Okay, so also so these things are the potential research domain that aid in lesser better prospects. So with this, we have come to this week's end of this week's discussion. So we'll have discussion on the questions and answers. So okay, so let's take a 2 minute break and then we can start on with the discussion of the question and answers. In the meantime, if the question is there, so you can ask directly. Okay. So let's begin with the question and answers. Further, if you have some discussions, we'll do accordingly. So functions of gate drivers. Yeah, I got it. Amplify the voltage level of PWM pulses coming from the controller. Isolate the control circuit from the power circuit. Both A and B, none of the above. Functions of gate driver circuits in an inverter. Amplify the voltage level of PWM pulses coming from the controller output. Isolate the control circuit from the power circuit. Both A and B, none of the above. Functions of gate driver circuit in an inverter are to amplify the voltage level of PWM pulses coming from the controller output, isolate the control circuit from the power circuit, both A and B, none of the above. So here we can see that the gate driver circuit's aim is to amplify the voltage level of the terminal control output as well as the output to isolate the control circuit from power circuit. So both are right. So option C is correct, both A and B. So now identify the correct statement. PI controller is used to regulate the current in the synchronous reference frame. PR controller is used to regulate the current in the stationary reference frame. PI or PR controller can be used irrespective of the reference frames and both A and B. So, so one of the statement is correct. Okay. So PI controller is used to regulate the current in the synchronous frame. One is synchronous reference frame, another is stationary reference frame. Anyway, PI controller is used to regulate the current in the synchronous reference frame. PR controller is used to regulate the voltage in the stationary reference frame. PI or PR controller can be used irrespective of their reference frames and both A and B. Anyway, PI controller is used to regulate the current in the synchronous reference frame. PR controller is used to regulate the current in the stationary reference frame. PI and PR controller can be used irrespective of their reference frames. So one option which is rejected is irrespective of the reference frame. So this is wrong. So but here for PI controller it can operate regulate the current in synchronous reference frame. And also here for the PR controller it is same for the stationary reference. It can regulate the current in stationary reference frame. So both A and B both are correct. Okay. DFIG. This is a question. So DFIG is capable of rotating in synchronous speed, subsynchronous speed, super synchronous speed, all of the above. This is an easy question. DFIG is doubly failed. GFIG is capable of rotating at synchronous speed, subsynchronous speed, which is also called supersynchronous speed is more. So after the blade, you have the shaft. So in the shaft, when it rotates after gearbox, then we have the generator. So we also have a feedback control. So using that diagram I'm talking about. So the feedback path is there to grid side converter, rotor side converter, DFIG. Initially it takes from the grid. After when it reaches the subsynchronous speed, it takes power from the grid. It so as to elevate the reactive power. So in this way, it can operate in all the modes. So it can operate as synchronous, subsynchronous, supersynchronous, all three are. So DFIG is what type of machine? Squirrel cage induction machine, slip ring induction machine, both A and B. None of the above. Squirrel cage, where we have the rotor bars. All of them are shorted. These are shorted bar. These are shorted bars. So based on electromagnetic induction, this first EMF is induced, and since the bars are shorted, the current starts flowing, and accordingly a torque is generated, which makes the machine starts rotating. Okay. So, what is the so it is a slip ring induction machine. So in case of squirrel cage, we won't have that control feature. Okay. So this is a slip ring induction machine where we can own rotor induction machine. We can also say where we have the rotor side control. Whether based on this rotor side, we can control from the slip ring machine. So number of cells connected in series provide a high current capacity, high voltage, high power, none of them. Cells connected in series. So what would be more in the output side? Current, voltage, or power. Cells connected in series. So what we get is that when we have connected in series, so overall the voltage increases. But when we here series, the voltage increases. The parallel current increases. So here it is series higher voltage. For n number of cells. Okay, so identify the correct statement. With respect to different types of storage elements. Supercapacitors can be used for cranking, diesel generator used for power backup. Incorrect statement. With respect to storage elements. Supercapacitors can be used for cranking of diesel generator used for power backup. Response time of supercapacitors is fast compared to lithium-ion batteries. In a microgrid, we cannot use two storage systems or elements such as lead-acid battery or supercapacitor together. All are incorrect. So, any guesses that supercapacitors? What is the incorrect statement here? Supercapacitors can be used for cranking diesel generator, used for power backup. Response time of supercapacitors is fast compared to lithium-ion batteries. In a microgrid, we cannot use two storage elements such as lead-acid battery and a supercapacitor together. All are incorrect. So here we have this one is the correct answer here. The power grid has demonstrated the smart grid technology capabilities in collaboration with various solution providers at which location? So power grid demonstrated the smart grid technology. New Delhi, Bangalore, Mumbai, Pune. So here it is. Pune. Which of the following is not the smart grid R&D area in the field of internet and communication technology and cyber security? Not. Threat models and cybersecurity, information privacy and handling challenges, cloud computing, data storage and big data analytics. ancillary services of converters. So now cybersecurity is another domain which is evolving with the mass integration of IT layer. OT layer was there, means operation technology. IT layer added a different problem. So overall, cyber threat and all these things are getting more predominant in the present day smart grid architecture. As we are trying to implement more and more system, integrate more and more system complications. So this was there, but due to this cyber threats doing much higher impacts, and for those things, threat models are being day by day updated. So researchers or R&D section needs to work on this, creating threat models and to understand threat models and accordingly present some cyber security to the grid. There can be attacks that we have discussed like denial of service attack, DOS attacks, or false data injection attack. At some note, information privacy and handling challenges that we observe some cloud computing, data storage, cloud computing, big data analytics, like the data analysis takes a major role in operation and control. So information privacy, handling challenges, all these things. So there is the ancillary services of the converters. Okay. This is not the part of smart grid R&D of ICT and cybersecurity. What is the need for energy management in microgrids? Manage renewables, battery, and the loads to reduce stress on the grid during peak hour, to obtain energy balance in an island operation, and all of the above. Manage renewables, battery, and loads. What is the need of energy management? What is the purpose of energy management? Reduce the stress on the grid during peak hour. Yes. To obtain the energy balance in an island operation. Any idea? Need for energy management in batteries, manage renewables, batteries and loads, reduce the stress on the grid during peak hour, obtain energy balance in an island operation, and all of the above. So here it is, all of the above, because to manage the renewables, batteries and loads, reduce stress during peak hour to obtain the energy balance and all of the above. So here it is all of the above. Charging of batteries is preferred during which of these models are mentioned below. Charging of batteries is preferred during which of these modes? Peak hour mode, excess demand mode, excess demand in case of isolated mode, peak hour or peak off peak hour mode. Any while guesses. Where would be the charging bit more preferred? These are peak hours. So charging would be preferred because we are in the aim to make this profile flat. So charging would be done in the off-peak hours. Okay. So off-peak hour mode is the correct answer. Right. So electric vehicle charging would be preferred in off-peak hour mode. Which of the following is a false statement with respect to power flow control strategy adopted for managing the energy for DC microgrid? Which of the following is a false statement with respect to the power flow control strategy adopted for managing the energy of the DC microgrid. Peak demand reduction, smooth transition between different modes, shortens the life of the storage system, unity power factor operation. So this is the fault. Shortens the life of the storage system. That is not being done. That is not the case here. Which of the following is feasible during the peak hour mode in the grid connected DC microgrid? Absorb as much power from the grid. Inject maximum power to the grid. Inject maximum available power to the grid. Integrate additional loads. Operate renewables in power dispatch mode. Is feasible during peak hour mode. As we have already seen, in peak hour modes. Absorb as much power from the grid. So during the already it is telling that these are the peak hours. So during this time, if more power is taken or absorbed from the grid, then the peak would rise rather than to fall. So this is not a proper choice. Okay. So our major aim is to now next is integrate additional loads. Similar is the case. Operate renewable sources in power dispatch mode. That's not so. Yes, so inject feasible. Inject maximum power available to the grid. So inject power to the grid. That would be uh, reducing the pressure on the grid side. Is in the islanded operation of the DC microgrid. Suppose the battery reaches its lowest SOC limit, which are the following actions preferable. Battery is allowed to drain out, PV is operated off MPPT, additional loads are switched on, non-emergency loads are turned off. Which of the action is preferable? So lowest non-emergency loads to be turned off. Full form SCADA that we all know previously have discussed supervisory control and data acquisition services. We all know. Oh sorry, this one is digital acquisition. I have told data acquisition but marked digital. And then the last one, in the case of islanded operation of the DC microgrid where the battery is completely charged, the source power exceeds the demand. Which of the following control is adopted for PV? Which of the, in case of islanded microgrid operation, DC where the battery is completely charged, source power exceeds demand, which is should be operated off MPPT. That's the only way out. So that's it. We are uh, done for this day discussion. So if you have any questions, we can discuss. Otherwise, we can wind up today's session. Meet on next Saturday. Okay. So okay. Thank you for joining.